Okay, let's we may as well jump into it. So last time we talked about gradient descent. This time I wanted to say a few more things about gradient descent slash how we, for example, prove convergence rates for something like gradient descent, or really just in general, because we went through that very quickly at the end. And I think I'm going to choose to not talk about gradient boosting, at least not now. So if we finish the subgradient lecture early, then maybe we'll talk about it. But I think it's worth not rushing and just skipping that, because it was kind of just, you know, supplementary. So I'll just mention like a couple sentences about it, and then we'll either push it to the end if we have time today, or we'll just skip it. So last time we talked about gradient descent, and we actually learned some facts about how fast gradient descent converges. We learned, let's say, this fact, which you're going to actually prove on your homework. And I'll mention, like, just so you get some intuition, a course overview of how we prove things about methods in general. So we didn't prove this in class, but you'll do it in your homework. This was kind of like the canonical result for gradient descent that you might remember, which is that if the function you're trying to minimize has a Lipschitz gradient, then we can take a step size that's smaller than 1 over the Lipschitz constant, or less than or equal to 1 over the Lipschitz constant, and we get that after k iterations, the gradient descent achieved criterion value minus the optimum is something like 1 over k. So it goes down at the rate 1 over k. Or said differently, to find a point for which this is less than or equal to epsilon, we need k on the order of 1 over epsilon iterations. Okay, so how might we prove things like this in general? So usually there's only a couple of steps to a convergence rate proof. So it's actually quite similar to what we did in the non-convex case, the proof of this. And the first thing you usually do is start with you know, some quadratic upper or lower bound on something like f of y around f of x. So let's suppose that x is the current point that we're looking at. That's the current iterate. So we usually start by saying that, you know, for example, if we have a Lipschitz gradient, then we get an upper bound on f of y. And that was actually the first step we saw in the gradient descent. That's interesting. I'm not sure why that happened. That was the first step we saw in the gradient descent proof of the non-convex case, right? And if we have strong convexity, then actually it's a lower bound. So we get, typically when we assume strong convexity, we also assume that it's Lipschitz gradient and plus strong convexity. So we get both the upper and lower bounds, but, you know, this gives us a lower bound on f of y. So that's usually the first step. And why do we do that? It's to establish some, I'll call it sufficient descent. Sufficient descent property at f of x plus. So this being the next iterate. So as an example, we saw in this case that when we plugged in for y the next iterate, which was x minus t times the gradient, we actually could simplify this right-hand side to say that the criterion at the next iterate was less than or equal to where it was at the current iterate minus something. Okay, and if we take t smaller than 1 over L, then this whole thing is actually positive. So it's minus a positive quantity. So if we take t smaller than 1 over L, actually this thing is itself bigger than a half. So this whole thing is less than or equal to f of x minus t over 2 times the norm of the gradient squared. So that's kind of like the, you know, as an example, e.g., this is what you do in your homework, in gradient descent with t less than or equal to 1 over L, we get something that looks like this. F of x plus is less than or equal to f of x minus t over 2 times the norm of the gradient squared. Okay, so that's typically, that's like a, an example of using the Lipschitz gradient upper bound to get some kind of sufficient descent. After one iteration, the criterion goes down by at least this amount. With strong convexity, by the way, you might ask why the lower bound is helpful. Seems like an upper bound on the criterion will be helpful for this property. With strong convexity, we can actually get something that, let's say, is much stronger. Of a result, we actually tend to get something that looks like this. X plus minus x squared is less than or equal to something in terms of, as an example, x minus the previous iterate. So we get a bound not on the distance to optimality in terms of the criterion value, but typically in terms of, or possibly even x star, let's say, the bound to optimality in terms of the solution or the iterate itself. And this actually comes from the lower bound that we get from strong convexity, because a quadratic term like this appears on the right-hand side, which then you can envision we use to upper bound something of this form. Okay, so whatever it is we're doing, we're either using some property of our function we've assumed, like Lipschitz gradient or strong convexity, to establish some sufficient descent property at the current, between the current iterate and the next iterate. Okay, it's either of the form in terms of f or the form in terms of the iterates themselves. And the last step is really then just to iterate or recurse this property to get a global statement about whether it be f of xk or xk itself. So that's really what almost every proof looks like that we'll see. Write down your assumptions, see what you can say about the function, establish some sufficient descent, iterate that property. And depending on what this looks like, we either get slower or faster rates. If it's of this form, we get what we call a linear rate. If it's of this form, we get a sublinear rate. And even in Newton's method, the proof will be similar to this in structure. It'll be also true with proximal gradient. It's just kind of the canonical way that we would prove rates. So I just wanted to give you that intuition, because last time we kind of rushed through it. With the non-convex case, we just took a bit of a detour here, and that actually made the proof easier, and that we realized that it was not realistic to assume that we could actually achieve, obviously, a global minimizer in terms of f. So we just looked for proving that the gradient got small, which we called a stationary point. And then instead of saying that f of x plus is less than or equal to f of x minus something, we actually just rearranged this to get a statement about the gradient itself. So it was just a bit of a detour, and actually the proof ended up being simpler from then on out. Okay, but then we still did the kind of similar in spirit third step, in which we iterated this bound over all the iterations to get a final answer. Okay, any questions about that general structure? Okay, I just wanted to mention maybe one thing that we'll revisit maybe as an advanced topic. I'm not sure yet. But you're looking at a statement like this, and you're saying that, well, we're saying that it takes 1 over epsilon squared steps to get an epsilon stationary point. And that's one in which the gradient, let's say in 2 norm, is less than or equal to epsilon. Well, you might think that's actually not a great result, because stationary points can look, there are actually various stationary points for a non-convex function, right? They can look like this. They can look like a local min, so that's stationary, right? The gradient is 0 there. They can also look like this, something of that form. the gradient 0 here. That's actually distinguished from this. This is called a local min. That's typically called a saddle point. Okay, and they can also be local maxes, right? So that's also stationary. So if you look at all of these, you might think actually only some subset of stationary points are actually useful. Like maybe a local min is useful, a local max or a saddle point is not. But this is not differentiating between them, right? This is just saying after epsilon iterations, we'll get to a stationary point. So just from that perspective, this result is pretty weak. But interestingly, there's been a lot of work on gradient descent in the last couple of years for non-convex functions. And I might mention some of this at the end of the course. But one result that's, I'll kind of just paraphrase, is that if you have a non-convex function that's sufficiently smooth, let's say has 2 derivatives, and you're doing gradient descent, then the set of points at which you would initialize gradient descent, and it would actually end up at a saddle point or at a local max, is very small. So you'd have to be very unlucky to end up at a local max or a saddle point with gradient descent if the step sizes were chosen, let's say, to be large enough with respect to the smoothness of the function. So most of the time, if you think about initializing maybe the algorithm randomly, we're going to end up at a local min. If we get to a saddle point, then we'll actually kind of blow through it because there'll be a spot of negative curvature. So we'll just keep going. And it's very unlikely, let's say, that we'll get to local maxes. So there, maybe even more precise statement is that the set of points that I would initialize them and get a saddle point or a local max have Lebesgue measure 0. So I'd be really, really unlucky to kind of end up there. And that paper is actually only a couple of years old that makes this statement. So in some sense, it provides more credibility to results of this type, right? That, yeah, this is really talking about stationary points, but the stationary points that we'd end up at are usually these guys, the local mins. Okay, well, my picture for gradient boosting didn't work, so that's already a reason why we should skip it. Huh, I don't know why. I think it should work when you pull up the slides on the web. But let me just say, maybe just one in 2 sentences, gradient boosting is effectively doing gradient descent on some loss function, like, for example, it could be for classification or for regression. So some supervised learning task where I have a bunch of features and I have a response. Could be classification, could be regression. But the loss function is smooth. That's why we're doing gradient descent. And the trick with gradient boosting is where we're going to we replace gradients with the closest approximation we can make with, let's say, a tree. So we're going to map gradients to let's say a vector of predictions given by a tree. So you could substitute tree here with any other kind of simple method. This is called a weak learner in the context of gradient boosting. But this could be anything that maybe you can fit somewhat efficiently. And the idea is that we're trying to solve a problem that's constrained. So we're trying to solve, let's say, find the best linear combination of trees to minimize classification error. That could be our problem. And that problem is actually too hard to parameterize. So the space of, like, let's say all trees of depth 5 is it's enormous. So it's too hard to parameterize. So what we do is we actually just ignore the fact that we want trees. We compute the gradient. So if we could fit anything to the data, what would be the kind of fastest descent we get on the criterion? We find that direction. And then we find a tree that aligns with that direction in terms of its predictions. So we say, let's find a tree that actually would give us close to that gradient. And then we add that tree to our collection. Then we repeat. We find the gradient. So this is the kind of, again, the direction of the fastest descent for minimizing the classification error. And that's just some vector, and we find a tree whose predictions are aligned with that. And we add that tree next to the gradient, to our collection. And we do that over and over again, and we get a big collection of trees. And we take some kind of linear combination of them for our final prediction. So I think it's quite a clever idea to do, some people call this functional gradient descent, but really it's just gradient descent for a constrained problem where we're kind of forcing the gradients to be part of our constraint set. And it's, I mean, you know, if you look at maybe machine learning at a slightly more popular, less academic level, gradient boosting is one of the things most people have heard of, right? It wins Kaggle competitions some large fraction of the time. Okay, so I mostly, wanted to spend today on subgradients. So even though we're in a unit on algorithms, this is actually like a brief pause to introduce a mathematical concept that we're going to use for subgradient method and for proximal gradient descent, which come for the next 2 lectures. So this is, again, maybe reintroducing a pretty core concept in terms of convex analysis. So I'll skip the summary. Today we'll talk about subgradients, which you can think about them as a generalization of a gradient for, we're going to focus on convex functions at points at which it's potentially not differentiable. And we'll talk about many examples and properties. There's a kind of a calculus of subgradients just like there was for convex functions and convex sets. And we'll see why they're useful. We'll see already, maybe for the first time in this class, a fully general characterization for optimality that we can state in terms of subgradients. So to motivate subgradients, we're going to remember this, this equivalent formulation of convexity that we learned for a differentiable function, right? So if a function is differentiable, then it's convex if and only if it lies above its tangent line everywhere, right? So if I take the tangent line at a point x, this is my function f, and this is, let's say, this is maybe the function f of x, if this is the point x, plus grad f of x transpose y minus x. As I vary y, that's this line. And we learned that for convex functions, this is actually a global underestimate of the function, right? The function lies above this line everywhere. And in fact, that was equivalent to convexity if we had a function that had this property that was differentiable. So a subgradient for a convex function, let's say, is really just any vector that has this property that we would get if we substitute out the gradient for that vector. So in other words, a subgradient of f at a point x is, let's say, g. So this is a vector of length n, just like the gradient would be, such that the same property holds. If we take the function evaluated at a point y, say out here, then we get that it's actually bigger than or equal to f of x plus g transpose y minus x for all y. Okay, so if the function is differentiable at the point x, then its gradient is certainly a subgradient, right? Because it does satisfy this condition. And in fact, if it's differentiable at the point x, then the only g that satisfies this is the gradient. So when it's differentiable, there's only one subgradient, it's uniquely the gradient. But if it's not differentiable, there could be many subgradients at a particular point x. And in fact, the same definition here works for non-convex functions. But for non-convex functions, subgradients actually need not exist. So let's see if somebody can give me an example of that. A non-convex function, let's say this function is even differentiable, but doesn't have a subgradient at some point. So you try to think of a function that, Okay, so that's true. So concave functions will definitely fill for us. So yeah, we can actually define an analogous quantity for concave functions that are a global overestimate of the function, but certainly we won't have the property that we're desiring. So a function, for example, like x cubed, if I take f of x equals x cubed, then this is smooth everywhere, and it has, let's say, a derivative at 0, of 0, in fact, but it doesn't, I can't find any line that would kind of globally underestimate the function. So I can have lots of examples of non-convex functions that are smooth everywhere and don't have subgradients. For convex functions, subgradients always exist. And there's one small caveat that I put as a footnote here, and that is they always exist on the relative interior of their domain. So if you look at the domain, which is the set of points for which the function is defined and finite, then on the interior of that domain, or actually a little more precisely the relative interior. Relative interior just means if the domain is maybe not full dimensional, then it's the interior with respect to like some kind of subspace on which the domain lies. But you can just think about it. So points that are away from where the function is infinite, we have subgradients. Hey, that's a good way to think about it. If the function is infinite at that point, then it's not. Then that point is not in the function's domain, and a subgradient need not exist. So that's just a very small caveat. But we typically don't talk about taking subgradients or gradients off the interior of the domain. And in fact, the proof of this, if you're curious, is really just an application of the supporting hyperplane theorem. So it's an application of one of these kind of core properties of convex sets that we learned. Okay, so I'm going to go through a bunch of examples, try to get us some intuition. So as the first example, let's just consider the function absolute value of x. Okay, it's convex. It's not differentiable everywhere. In fact, it's not differentiable at 0. And if we look at, let's say, any point that's away from 0, then we should imagine that there's only one subgradient, or in this case subderivative because we're in one dimension, and that's equal to its gradient or its derivative, right? So if I look like out here, then the subgradient is just the gradient, which is just 1. It's just going to be the derivative of the function x, right? And if I look out here, it's going to be minus 1, which is the derivative of the function negative x. So even geometrically or pictorially, you can think if I'm forced to kind of create a linear under-approximation to my function that passes through a particular point out here, I have to just take the line y equals x itself. I can't get that under-approximation any other way. And that would force g, the subgradient, to be 1. Same with out here. In the middle here, okay, I can actually take a slope of anything between minus 1 and 1 and still get a global underestimate of the function. Right? If I look at a line passing through 0, its slope can be anything between minus 1 and 1. And any of those would actually give me the property that I desire, which is this property here. Right? The function lies below that line. So the subgradient at 0 is actually any element of the set minus 1 to 1. So it's anything between minus 1 and 1 inclusive. You could also prove that from the definition, but I think for these types of examples, we can just kind of look at them and try to reason geometrically. So let's consider a slightly more complicated function, which is just the norm of x in 2 dimensions. Well, actually, this picture has it as being 2 dimensions, but let's say this characterization here is just treating the dimension n as general. So here's a picture of the norm of x in 2 dimensions. And from what you can hopefully remember from multivariate calculus, if I were to, let's say, differentiate this function away from 0, then it is differentiable. And in fact, its gradient is just x over the norm of x. Okay, you can get that even without even needing to resort to multivariate calculus. Just write out the norm in terms of the sum, the square root of the sum of xi squareds, differentiate with respect to xi, that would give you the ith entry of the gradient, right? Xi over the norm of x. So it's differentiable away from 0. This is its gradient. And as we mentioned before, that's going to be uniquely its subgradient as well. Okay, if I'm at 0, the function is actually not differentiable. You can actually see that just by looking at what its derivative is away from 0. Right? This is not really going to be defined as I move towards 0. But we have a subgradient at 0. And in fact, the subgradient is any element of the unit ball. So remember, subgradients they're of the same dimension as the gradient would be. Right? So this has to be an n vector. And if I take any n vector that has L2 norm less than or equal to 1, that is a valid subgradient. So it's a little bit harder to see geometrically, but here we can just check the condition, right? The condition is this. So we need this to hold in general. And if we take x equals 0 and we take f to be the norm of x, then we get the following. Right? And now we can just see directly, let's say, from Cauchy-Schwarz, that this is going to be satisfied if and only if the norm of g, so any g such that the norm of g is less than or equal to 1 will work. Okay, so that's how we would characterize, for example, the subgradients of the L2 norm at 0. Okay, so just moving on, we can talk about the L1 norm now, slightly more complicated of a case. So here's a picture of the L1 norm in 2 dimensions. Now it's actually not differentiable at along any one of the coordinate axes. Okay, you can also see that by writing this out as the sum of absolute value of xi. If xi is equal to 0, then this is not going to be well defined. It's not going to be differentiable for the same reason that this wasn't differentiable at 0. Right? So as more points of non-differentiability. And we can treat this in a couple of ways. But let's think about the subgradient in each component. So again, the subgradient is an n vector. It's of length n. Let's think about its ith component, when that's unique and when it's not. If xi is not equal to 0, then the ith component is unique, and it's just the sign of xi. It's the exact same story as we saw here. Right? If this univariate argument is not 0, then the subgradient is just the gradient, which is just the sign. And if it is 0, then it's anything between -1 and 1. The same story here applied component-wise. Right? So we're going to have the ith component is unique if the ith component of x is not 0, and it's the sign of xi. And otherwise, it's anything in between -1 and 1. Okay, so these give us all of the subgradients then, any g's that satisfy these properties. And one last example. All of these examples, by the way, we're going to see kind of generalizations of how we would compute these with kind of more generic rules, but we're just doing this to get some intuition. Let's suppose we have 2 convex functions. They're both differentiable, and I take their max. So this we know from our rules about operations that preserve convexity is itself a convex function. Okay, f here, which is the pointwise max of f1 and f2, is convex, if these two are both individually convex. And here's a picture. Let's say maybe I had one convex function that looked like this, another convex function that looked like this, and I took their max. Each of these 2 functions individually were, let's say, smooth. Their max need not be smooth. That's what this solid line is displaying here. And we have to divide our arguments into, let's say, a few cases. If we're looking at at a point x for which, let's say, the first function is bigger than the second, maybe it's out here, then in fact there's just one subgradient, and that's the gradient of f1 at x. Right? How do you reason that's the case? Well, let's say if f1 of x is strictly larger than f2 of x, then you can think about, in a neighborhood of that point x, this function, which is the max of the 2, is just f1. Okay, so in some small neighborhood, it's just the function f1. And so asking for a subgradient in that function because f1 is differentiable, is like asking for a gradient. And so there's just going to be one answer, which is the gradient. If I'm at an x for which f2 is strictly larger than f1, which is somewhere out here, it's the same logic applied in reverse. In a small neighborhood around that point x, I'm just looking at the function f2, right? Because the max of f1 and f2 is just f2 in some neighborhood. So again, the subgradients are just going to be the gradients of f2. So there's just one, and it's the gradient itself. So the only case we haven't covered is x for which we have an equality, which is something like this, when two of these functions are equal, when f1 is equal to f2. And in that case, I claim that there are infinitely many subgradients. Okay, if let's say the gradients of f1 and f2 don't match, and any point on the line segment that joins the gradient of f1 and f2 is a valid subgradient. Okay, so I can take, for example, 1/2 of the grad of f1 plus 1/2 of the grad of f2. That's a subgradient. I can also just take grad of f1. That's a subgradient. I can also just take grad of f2. That's a subgradient. But any convex combination of these two gradients will give me a subgradient at points for which the functions are equal. So that you can prove this right from the definition, just as we've done, let's say, with this. It's just writing on the definition and seeing when that property is satisfied. It's also a special case of a more general rule that we'll mention in the slides that you'll prove is valid on the homework. So you can take a slightly more general view and look at this general rule to construct subgradients of maxes of functions. Yeah?
Just, how do you make the argument that there exists a neighborhood image? That's like the technical.
Yeah, that's a good question. So that's actually not needed for the homework proof. That was mostly used for intuition, but it's a good question. So there are a bunch of let's say, analysis properties of convex functions that we haven't covered. So one property of convex functions that I haven't covered that's intuitive, I think, is that convex functions are continuous on the relative interior of their domains. So you can't construct a discontinuous convex function unless that discontinuity is somehow on the boundary. So it's intuitive. It turns out not to be an easy thing to prove. But it's a very nice property of convex functions. If you try to restrict yourself to convex functions and give it a jump somewhere, you'll learn that you're going to break the property for convexity. So I kind of was implicitly assuming that when I made that neighborhood argument. So. Okay. So just moving along. So some more notation or nomenclature. The subdifferential is defined as the set of all subgradients of a function at a point. And we denote it by partial of f at x. So it's any one of those g's that we were talking about that is a valid subgradient. It's non-empty for convex functions. And again, there's this caveat that, it is important somehow to point it out, but you can kind of ignore it. I just don't want to give you false information. It's non-empty on the relative interior of the domain. Okay, so which is typically the points x that we think about. It's actually always closed and convex, kind of an interesting property. This is true even for non-convex functions. So for non-convex functions, the subdifferential could be empty, right? We could have no subgradients. But it's always closed and convex. So the empty set is closed and convex, kind of vacuously. But even when it's non-empty for a non-convex function, the subdifferential itself as a set is always closed and convex. So if I have any two valid subgradients, then their convex combination will also be a valid subgradient. That's always true. If f is differentiable at x, then the subdifferential only has one point, and that's the gradient. We already kind of learned this, right? That when it's differentiable and convex, gradients and subgradients are the same. And conversely, if there's just one element of the subgradient, or of the subdifferential, so there's only one subgradient, then it must be differentiable. And that is its gradient. So this is sometimes an interesting way to prove that, for example, that a function is smooth. If you have a convex function, you want to prove that it's smooth. You could actually try to characterize the vectors g for which this holds, and if you can prove there's only one g for which this holds, that actually proves that it's differentiable, and that's its gradient. So that's sometimes an interesting way to prove that's a function is smooth, a convex function is smooth. So there's an interesting connection between subgradients in convex geometry. I told you what the normal cone was before, and I figured I just would maybe point out the connection now. So let's consider taking subgradients of indicator functions. Okay, we saw that an indicator function of a convex set was a convex function. So let's suppose we have some set C convex, and we're going to define this indicator function, right, to be 0 if the point x is in the set and infinite otherwise. And we're going to ask, let's say for points that are in the set, what are the subgradients to this function? And it turns out that it's actually something familiar to you, or a little bit familiar, because at least I mentioned it a couple times, which is the normal cone of the set C at the point x. So it's the set of all vectors for which if I take the maximum inner product over all points in the set C, it's maximized at x. So I have this property. G transpose x is bigger than or equal to G transpose y for all points y in the set. And the proof is very simple. It's like just peering at the definition. And I have to check when this condition holds. Let's say when x is in the set for all y. So I want to check that this is true for all y, and I'm told that x is in the set. Right? So that's actually equivalent to this, because that's 0, because x is in the set. And so now we just consider two cases. If, let's say, y is itself in the set, right, then this is 0. The indicator function at y is 0. And I get that 0 must be bigger than or equal to G transpose y minus x. But that's exactly the condition for the normal cone, right? That I get G transpose x must be bigger than or equal to G transpose y. And if y is not in the set, then actually this condition is immediately verified because the left-hand side is infinite. So there's nothing I need to, there's no other conditions I need to place on G to make this true. It's just vacuously true. Right, so the set of G's for which this holds for all y is actually exactly the set of G's for which this holds for all y, which is just the normal cone. That's how we define the normal cone. So here's a picture. I'm trying to visualize what the normal cone looks like for you at various points on the boundary of this convex set. Okay, and actually, to be perfectly clear, I'm showing you the normal cone translated. So the normal cone is a cone, which means it must contain 0. So actually, all of these things I'm drawing for you, they really should emanate from 0. But just for intuition, I'm actually translating it so that it emanates from the point at which I'm evaluating the normal cone. So let's just pick one of these. I think it'll make, hopefully, some sense. So let's say this is the point x. So the normal cone is the set of all vectors for which if I took the inner product with all points in the set of that vector, it's going to be biggest at x. Okay, so you can think about that as being precisely vectors that are pointed in this direction. Right? If I had a vector point in this direction, then I could make that inner product, let's say this was 0, largest with the point x out of any points y in the set. Right? Any of these y's are less aligned with this vector than x is. Okay, and similarly, let's say if this was my point x prime, then the normal cone is going to be emanating in an orthogonal direction to the boundary, because if I were to take an inner product with any vector that was pointed in this direction, it's going to be biggest at x prime versus all other points y in the set. Right? It's better aligned with x prime than it is with, like, say, this value of y. And so again, just to be clear, the normal cone is actually any vector that's pointed in this direction. So it's any positive multiple of this vector, but I'm just drawing it to be translated so that it actually emanates from the boundary itself. I think that's just for intuition. And let's say at this point, the normal cone is actually anything It's actually a proper two-dimensional cone in this example. So it's any vector that's pointed in any direction between, say, these two extremes. If I had, let's say, a point x double prime out here, then any of these vectors will have maximal inner product with x double prime versus any other point y. And that's what the normal cone, that's how we kind of intuit it. And in fact, these are just subgradients of the indicator function. So maybe just for a bit more intuition, what happens if I ask for a point that, why am I drawing points in the boundary? What happens if I ask for the normal cone at a point in the interior? Like, let's say this is x triple prime. What is the normal cone at that point? Yeah, it's just the normal cone in this example at x triple prime is just 0. So it has to always contain 0. It's a cone. But it can't contain anything more than 0, because if it's in the interior, then I can always find a vector. Let's say if you give me any vector at all, g, I could always find a vector that has a greater inner product with g than x triple prime does. Because everything in a ball around x triple prime is still in the set, because it's in the interior, and one of those will be better aligned with, let's say, the g you chose. So it's kind of vacuous on the interior, which is why I was drawing on the boundary. Okay. I think it's worth maybe going through the subgradient calculus, and then we'll take a break after that. So here are some useful rules we have for subgradients. There are more as well. It turns out that they just get more complicated. So if you're interested in more complicated rules for subgradients, you can come talk to me. But here are some of the simpler ones. So if we have any convex function and we scale that convex function by a scalar, then the subdifferential of the function a times f is just a times the subdifferential of f. So it's important here that a is positive. Why is that important? What happens if a was negative? Right, then I would make this function concave. So it's important we're talking about positive scalars here. And by this I just mean take every element of the subdifferential and multiply it by a. If we have two convex functions and we add them, then their subgradients are just the sum of their subgradients. It's also very important that I'm talking about convex functions here. You can think about adding two non-convex functions to cancel out their non-convexity in some way, and then you get subgradients of their sum. But individually, they could have no subgradients. So these could both be empty. Right? So it's, again, really important we're talking about convex functions here. So just like we have the chain rule for gradients, we have a kind of chain rule for subgradients. But for simplicity, I'm just presenting it to you when you compose a function with an affine function. So if you have a convex function f, and I'm composing it with an affine function ax plus b, and I'm calling that function, let's say, g, then the subgradients of g are just a transpose the subgradients of f evaluated at ax plus b. So this reduces to the chain rule that you know, right? If I replace this partial sign with a nabla, with a gradient sign. This is just what you know for gradients, but a little more general. Okay, so hopefully all of these should make sense. These should be things that, are almost second nature from what you know about gradients. Here are some properties that are a little bit... Oh, did you have a question?
What happens when you compose two convex functions which happen to be convex?
Yeah, that's a good question. So the composition rule for general functions, we need to place conditions on the function so that the composition is convex. So for example, the outer function could be convex and monotone. Inner function could be convex. And then it is actually just this. It's going to be exactly what you would expect from kind of the chain rule. But there may be a little bit of technical conditions we need to place to make sure that we're never leaving the interior of the domain in all those evaluations. But if you're kind of, let's say, in the interior of the domain, it's just what you would expect from the chain rule.
How do you take the product of set.
You take any element of one, and any so one will be. Let's say if they're both vector valued, you take any element of one element, any element of the other, and you take their inner product. Other questions? Okay, so these are just kind of, like I said, maybe what you expect from gradients. This one is a little bit more exotic, but it's very useful. That's a very useful property. If we have a maximum of convex functions, just like we had in that previous example, we had f1 and f2. Here I have m functions, f1 through fm. They're each convex. And let's say I'm denoting f to be their pointwise maximum. Then the subgradients of f at a point x are given by the following recipe. First, find all of the functions fi that achieve the maximum. So that's these guys. So it could just be one function, could just be that the maximum is achieved at f1, could be many functions, f1, f2, f3. It could be some collection of functions. But find all of those functions. And we're going to call those active functions. There are functions for which they achieve the max in defining f. For each one of those functions, take their subgradients at x. So that's what we have here. Okay, and if they're differentiable, that's just the set containing their gradient. But it could be not a singleton. Take the union of all of those. So I throw all those subgradients together and take the convex hull. That is the subdifferential of f at the point x. So we know that somehow this has to be here in the end because the subgradient, the subdifferential is a convex set. Right? So if I just had a bunch of things I was claiming was in the subdifferential, then since it has to be convex overall, I'm going to have to take a convex hull, right, of this union. This actually describes all of the subgradients as well. So I think to remember this, it maybe helps to remember this rule here, this one we talked about, because it reduces to this in a simple case. Let's just suppose that, let's just suppose I have f1 and f2, and I have x such that f1 of x equals f2 of x. Then if I look at the union overall functions I such that fi equals f of x, then that's just going to be something separate for the first and for the second function. And in each case, remember, in that example we talked about these were differentiable. So the subdifferential just contains the gradient. So if I ask you to find the subgradients of either function fi at the point x, there's only one, and it's the gradient. So that's the subdifferential of these functions at the point x. And if I only have two i's here, and I take the convex hull of this set, then that's just actually the line segment joining these two gradients. Right? Each one of these unions just contributes a singleton. Looks like this, and the convex hull is just this line segment. So it reduces to the rule that we had learned before, just more general. Okay. I'm going to continue on to maybe the last property, and then we'll take a break, which is the general pointwise maximum. So here we had the case where we have finitely many functions. You could ask, what happens if I'm maximizing over a potentially infinite set of functions? So I'll index it by, let's say, s, and I'm going to define f by maximizing over all s, fs of x. So each one of these are functions. Let's say they're each convex. That's how I'm defining f of x. So from what we already saw, this function is convex itself if each one of these functions fs of x is convex. And the rule is actually very similar to what we had before. Just find all the functions s for which they achieve the max, take their subdifferentials, take the union, take the convex hull. There's just there's kind of two slight caveats. One is that we need to take the closure of this set. So this set actually need not be closed if this union is infinite. some pictures you could draw yourself to try to convince yourself of that case. But the subdifferential is always a closed convex set, so we need to kind of make it closed and convex. We're taking the convex hull. We're taking, at this point, the closure. And in general, all of these are subgradients, but they need not describe all subgradients. There still could be some that we're missing. So the subdifferential at least contains these. And typically, whenever we use subgradients, we just want to know how to compute a subgradient. And so this is still a useful rule. These are all valid subgradients. There just may be others. And under some conditions on, let's say, the set S and these functions f of s, we actually get an equality here. So one important special case in which we get an equality is actually in the dual representation for norms. So let's say S is compact, a compact set, and each one of these functions fs is continuous, then this is we get an equality here. That's like a sufficient condition. So an important special case is for norms. This is the one that we'll be using this rule the most for. And there's something that we call the dual representation of an LP norm that we'll treat a little more formally later in the course. But remember, the LP norm is defined like this. I just take the pth power of the absolute values of each of the xi's, and I raise the sum to the 1 over pth power. And if p is, let's say, bigger than 1, then we know this is convex. And we can define a q such that 1 over q plus 1 over p equals 1. Okay, this is always going to be possible, let's say, if p is larger than 1. P is bigger than or equal to 1. It's always possible. And it turns out that actually we can also represent the p norm as the maximum over all points y, such that the q norm of y is less than or equal to 1 of y transpose x. This is called the dual representation of the LP norm. And to get some intuition, you could think about the case when p is 1 and q is infinity. Okay, that should explain to you somehow why this is possible, as an example. Or you can take p equals 2 and q equals 2. Both of those cases, I think, are intuitive. But in general, we can think about this representation as being something of this form. Okay, I'm taking a maximum. So here I have y as the index instead of s. And the set S is exactly the set of all y for which the L2 norm or LQ norm of y is less than or equal to 1. Right? So I'm taking a maximum overall y in this set of this guy is my fy of x. It's y, just simply here y transpose x. And in this case, we actually get that this rule describes all of the subgradients. And in fact, this reduces to something very simple. The subgradients of the LP norm at a point x are just all of the values of y, I guess I had z on the slide here, that achieve the max. So this is our rule for subgradients of convex LP norms. It's just all of the points for the LP norm, all the points z that have q norm less than or equal to 1, such that z transpose x achieves the max. It's the argmax. Okay, maybe I'll let you reason how to get that from here on your own, but it's just interpreting. I mean, it's really very simple. It's just taking subgradients of each of these with respect to x, and then essentially that's all you need to say. But that's one rule that is a nice kind of thing to remember. Okay, let's take a quick break, and we'll come back and talk about how we use subgradients and why they're important. So you might ask, why are we wasting our time with subgradients? It seems like we've spent a while talking about something that's rather mathematical, but I think subgradients are one of the most vitally important kind of tools you can understand for convex optimization, and there's basically two uses for them. The first is that we can often use subgradients to characterize optimality. And we're going to actually see that in this lecture, but we're going to more generally see that when we talk about the KKT conditions. So it's a very useful tool to have to talk about optimality conditions for convex problems. And the second reason is a more practical one, which is that if you can compute a subgradient of a function, then you can minimize it. Okay, it might not be fast. It could be very slow. And in fact, next lecture, so on Wednesday, we'll talk about the subgradient method, and we will establish its convergence rate. And it won't be fast, but still, it's the most general way to minimize, let's say, a convex function. So if you understand subgradients, it's kind of like the biggest hammer you have to minimizing a convex function.
All the subgradients are
just a subgradient. So we don't need to characterize, let's say, all of the subdifferential. We just need to know how to compute a subgradient. Okay, so let's start off with optimality. This is so simple. You're going to look at me like I'm pulling a sleight of hand here. But for any function, convex or not, any function in the world, if I'm at a point x star that achieves the minimum, that's equivalent to 0 being a subgradient of f at x star. Those are equivalent statements. So if I can compute subgradients of my function, I just need to check whether 0 is in it. Okay, and in general, that could be very hard, but for convex functions, through the rules we learned, it should be more tractable. Right, if I can check whether 0 is in the subgradient, that's equivalent to checking whether I have a minimizer of my function. This is sometimes called subgradient optimality. It's very general. In some sense, it kind of precedes the KKT conditions that we'll talk about later. And let's see why that's true. It's super easy. The proof is one line. This is, if I put a g here, that's the condition for having a subgradient at the point x star, that this is true for all y. But if I take g equals 0, right, then this just reduces to f of x star. So f of y is bigger than or equal to f of x star for all y, if and only if 0 is a subgradient. Okay, that's the whole proof. So the implication, let's say, for a convex and differentiable function is something that you are familiar with, say, from previous courses, that minimizing a convex and differentiable function, I can just take its gradient and set it equal to 0, because that is the only subgradient. Right? So it just generalizes what you knew before. Now we can check whether 0 is in the subdifferential of our function. So we're going to use this in a couple of ways, and I'm going to show you how we can use this to derive the first order optimality condition that we saw a couple lectures ago. So remember I said that if we have a problem that is minimize a smooth convex function subject to x lying in some constraint set C, then if I look at this condition, this is equivalent to having x that minimizes, that solves this problem. Right, minimizes f subject to this constraint. And that it's basically, the way I think about it is that if I'm at the point x and I think about moving to a point y, for any other y that's feasible, it's in the constraint set, then the gradient at x should be telling me that's a bad idea. It should be telling me that I'm going to only increase the function by doing so. So it's aligned with the vector from x to y, because this is non-negative. So this is equivalent to having solved this problem, and we're going to actually derive this from this condition, from that. So let's do a couple things. First, let's recast this problem as just minimization of an unconstrained function by writing this constraint as an indicator. Okay, so we're going to say we're going to minimize over all x, f plus the indicator. And when x is in the set, we'll get 0 here, and when x is outside the set, we'll get infinity. So it's going to effectively enforce this constraint. And now let's just apply subgradient optimality. We have to check whether 0 is in the subdifferential of f plus the indicator. Okay, and if we can do so, then if we can find the x's for which that's true, then those will be the minimizers of this problem. So first, we can apply the rule, actually, that to take the subdifferential of f plus the indicator, these are both convex, and the subdifferential is just the sum of their subdifferentials, right? I can take the subgradients of f and the subgradients of the indicator and add them up. And for f was assumed to be smooth, so actually its subdifferential is just the set containing its gradient. That's the only subgradient there is. And for the indicator, its subdifferential is its normal cone, which is what we just saw and proved a couple slides ago. Okay, so 0 being in the set, which is a singleton, it's the gradient plus the normal cone, is equivalent to the negative gradient being in the normal cone. Right? These two statements are equivalent. Right? Because if I can get 0 by taking the gradient and adding it to something in the normal cone, then the negative gradient must be in the normal cone. And just applying the definition of the normal cone, this says that if I take the inner product of this vector, let's say g is minus grad f. If I take the inner product of g with x, it must be bigger than or equal to the inner product of g with y for all y in the set. That's the definition of the normal cone. Just applying that definition here. And simply rearranging, so just let's say moving this term minus grad f transpose y to the left-hand side, we get this first order optimality condition. Grad f of x transpose y minus x must be bigger than or equal to 0 for all y. So we've recovered this intuitive first order optimality condition. And I'll just mention that actually if we just relaxed the assumption that f was differentiable and we just said it was convex, then we would essentially be using this as a condition for optimality. Just replace where we had the set containing the gradient with the subdifferential. This is actually a fully general condition for characterizing optimality in convex problems, because we saw we could express any convex problem as minimizing some convex function subject to x being in some convex constraint set. This could encode a bunch of inequality and equality constraints on other functions. And by writing this as an indicator and applying subgradient optimality, we've actually characterized optimality in general. And the reason this isn't the end of the story is that this is typically a hard condition to work with. Okay, this is just typically not that easy to mechanically manipulate when you have functions you care about. It's not easy to compute the normal cone, and it's not necessarily that easy to try to satisfy this condition. So this is where the KKT conditions come in, which are actually equivalent to this, but just are essentially a reformulation of this. They're just easier to work with for constrained convex optimality. Okay, so we're going to go through a couple of examples of how you might use this subgradient optimality, and the first is the lasso. So we'll look back at the lasso problem, which gives us a sparse estimate of the regression coefficients. We're using the penalized form here, which we've seen in the previous lecture, and we're going to try to compute a subgradient of this criterion and set it equal to 0, and see what we can learn, because that will tell us that we actually have a solution at that point. So taking a subgradient of this criterion, well, again, these are both convex functions. I can take their subgradients and add them up. This guy is actually differentiable, and its gradient is x transpose the quantity x beta minus y. But here I've just written this as minus x transpose the quantity y minus x beta. This is the thing I said you guys should get really familiar, taking gradients of the least squares criterion. And the L1 norm, well, times lambda. So first we can pull lambda out. That's just a positive scalar. We saw that rule already. And we can multiply it by the subdifferential of the L1 norm of beta. But we also computed what that was as one of our earlier examples. Right? Basically, in the ith component, that's either going to be the sine of beta I or anything between minus 1 and 1, depending on whether or not that beta I was 0. So let's just call v some element of the subdifferential for shorthand. Then this rule is that x transpose the residual, y minus x beta, is equal to lambda times v. For some v that satisfies the following equations, it's 1 when beta I is positive, it's negative 1 when beta I is negative, and it's anything between -1 and 1 when beta I is 0. So if we can just slightly rewrite this. I'm going to let xi denote the columns of x. I'm just going to look at this equation component-wise. So look at it in the ith component. That says that xi transpose the residual, y minus x beta, must be lambda times the sine of beta I, if beta I is not 0. And otherwise, it must be equal to lambda times anything between -1 and 1. So equivalently, I can say that the absolute value of xi transpose the residual is less than or equal to lambda when beta I is 0. So this is subgradient optimality for the lasso. I think it's actually very intuitive if you think about it from the perspective of regression. It's saying that somehow if we look at the correlations of variables with the residuals, for the ones that I've called non-zero, that should be maximal in absolute value. These guys should all have correlations lambda or minus lambda. And for the other ones, I'm willing to not include that variable if the correlation with the residual is smaller in absolute value. So I think that they're intuitive. They don't give us a way to write down the lasso solution in closed form. Okay, we don't have a closed form solution. We can't really go much farther than this. But they do lead to a lot of other things. For example, I think I already mentioned to you that they lead to a proof of support recovery under some kind of model conditions. And even much more simply, they lead for us, they give us a way to check lasso optimality. So if somebody says, here I have this beta, it's a solution, you can check it by just checking these conditions. Okay, if the inner product of xi with the residuals is indeed lambda or minus lambda for all the betas that were non-zero, and for all the betas that were 0 is less than or equal to lambda, then that's a check that we have a solution. Okay, and they're also very helpful to develop one thing that we call screening rules, which I hope to cover later, which gives us a way to actually throw out variables from a lasso model without having solved the problem at all. So if we could, let's say we could certify that at the solution we knew this was the case, that the absolute value of xi transpose the residual was strictly less than lambda, then we can already say a priori that that beta I will be 0. Right? If we could ensure that at optimality we get a strict inequality here, then we know that actually that variable is not going to be in the model, because of the fact that if it was, then we'd have to have it being equal to lambda or minus lambda from the KKT from these subgradient conditions. Okay, so just reading off a bunch of facts there. I have 2 more examples, although I think I really only wanted to cover the soft thresholding one. The other one we can skip. So the soft thresholding example so I'm looking at a version of the lasso problem where the design matrix, or this matrix X, is the identity. So I'm just going to be looking to minimize overall beta, the squared norm of y minus beta squared plus lambda times the L1 norm. And this is a case in which actually subgradient optimality directly gives us a solution to this problem. And it's called soft thresholding. That's the name of that we give to the solution. So essentially, we just take every entry of this response, or this target y, and we compare it to lambda. And if it's bigger than lambda or smaller than minus lambda, we just move it to 0 by an amount lambda. And if it's between minus lambda and lambda, we set it equal to 0. So that's why we call it soft thresholding. We set it equal to 0 if it's smaller than lambda in absolute value. Otherwise, we move it to 0 by an amount lambda. And we can derive this as the solution to this problem, okay, directly using subgradient optimality. And let's just go back to these conditions in the case when x was the identity. Okay, if x is the identity, then actually these become the following. In every component, I have to have yi minus beta I being equal to the sign if beta I is non-zero. And otherwise, it has to have absolute value less than or equal to lambda. And because these conditions actually decouple over all I can just try to compute the solution for one I individually, and that'll be good enough, right? These conditions apply component-wise. So there's no reason to think about this as a problem over n variables. So let's just look at one I and try to verify this condition with, say, this particular form for beta. So we're just going to plug in. I'll write these conditions here. We're going to plug in beta I equals soft thresholding at the level lambda of yi. And we're going to try to check these conditions, which is that yi minus beta I is equal to lambda times this sign, or is less than or equal to lambda in absolute value if beta I is 0. So let's just break it up into a few cases. Let's suppose that yi was bigger than lambda. Then beta I is going to be yi minus lambda. That's what the soft thresholding operator would do in this case. Okay, and this is actually going to be bigger than 0, right? Because I've assumed y is bigger than lambda. So I should be trying to check this first condition. And in that case, yi minus beta I, it's just going to be equal to lambda, which is in fact equal to lambda times the sine of beta I. Right? Because beta I is positive in this case. If yi is strictly less than lambda, or minus lambda, then it's similar. It's just the reverse argument. We're going to find that yi minus beta I is going to be negative lambda, which is lambda times the sine of beta I in this case. And if yi is in between minus lambda and lambda, okay, then beta I is going to be 0. Soft thresholding will set that equal to 0. Right, so I should be trying to check this condition, the second condition here. But in this case, it reduces to just checking that yi is less than or equal to lambda. Right, and that is kind of immediately done for us via this condition. And if we look at reversing these arguments, you would see that actually we would derive soft thresholding by considering these in cases. If we consider these in the cases when yi was large, or large or small negative, or something close to 0, we would have derived soft thresholding just by reversing these arguments entirely from the KKT conditions. Okay, that's all I wanted to say. I think we don't need to cover this last example. It just was another example of how to compute subgradients for a somewhat complicated function. I'll just tell you the answer, and then we can go home. So if we have a closed convex set C, and we look at the minimum overall y in the set of the norm y minus x, then that defines as a distance function. Right? So if that's a point x, and this is a set C, then this is measuring us the distance between x and C. So this example computes subgradients view of this convex function. And it's an interesting example in which if you compute the subdifferential, it only has one element. And that element is actually just the difference between x and its projection onto C, which is this point, divided by its norm. So provided that x is, let's say, not on the set already, or not on its boundary, this is going to be positive, and so this is well defined. That actually, because this is convex, proves that this is its gradient. So if I told you to prove that this function was differentiable, like for x outside the set, it's not an easy task, and certainly not if you approach it kind of from first principles. But if you recognized it was convex and you computed its subgradients, you'd find there was only one, and it was this guy, and that implies that it's smooth. So if you're curious, the details are in the slides. Okay, see you guys on Wednesday when we'll talk about the subgradient method.